Okay.
All right. Welcome to post FTC day. It is Monday. We learned about the FTC on Thursday. Then we got a little test on Friday. Post FTC day is really important. It's almost as important as FTC day. I would say this is the second most important day of your life. The first being FTC day, the third being pre-FTC day. And today is a day where we actually learn what it all means. So what does it all mean? Can we just have a, what's that called? Share, parent, what's that called when you just like talk about your feelings? Steven, FTC day on Thursday, what were your thoughts?
I was pretty shook.
I was sort of disappointed with the...
Just cutting off Steven in the middle of his sentence.
Yeah.
Steven, you were saying something positive, potentially sarcastic, not really sure.
Mind-blowing.
It was mind-blowing, yeah.
I was disappointed.
You were disappointed because?
Because
You thought it would be more.
Yeah, like it just, like I already knew that. I felt like I knew that subconsciously.
Interesting,
like,
yeah. That is a reaction that some people have where they think, wait, what's actually new here? Is this really, this is almost like sort of like, I almost kind of like knew this already or something. And some people might still not get it. You might have just like, oh, okay. It might be today actually where you start realizing, oh, okay, see what's happening so far. Anyone else have something important they want to say? Oh, the juniors, we had our own special FTC day with just juniors. We had, it was a dignified and refined FTC day with tablecloth, candlesticks. We had Korean barbecue also, so.
Wait, what? How? Wait, when?
We're great.
Exactly. All right. Yeah.
Where?
So, right here. We have pictures.
No.
When you guys were taking like an AP or something. All right. So, what is the fundamental theorem of calculus? Let's have this conversation. The fundamental theorem of calculus comes in two parts. There is what I call the real FTC and what I call the useful FTC. I don't know, which is your favorite?
Useful. Real.
The real FTC, what I used to call FTC Part 1, says that if you take an accumulator function and you start integrating at a and you stop integrating at x of some particular function f, and then you ask the question, okay, at what rate is this integral increasing? Then the answer is, for a particular x, the rate at which this function is increasing is actually just the value of the function at that point. It's amazing. And then FTC, the useful part, the useful FTC. This one says that, well, if you want to take the integral from a to b of the derivative of some function, then the answer is it's just f of b minus f of a for that function. This is in some sense kind of crazy. And in fact, let's take a particular integral, which prior to the FTC we might not have known how to do at all, the integral of sine. So okay, suppose I want to know what is the integral from 0 to pi of sine x. Okay, I can draw this, and if you're integrating sine, you should probably try to make it look kind of right. So like, does that look about 3 times as much? I feel like it looks about 3 times as much, yeah, maybe. So sine kind of looks like this, like that. And I want to know how much area is under this curve. So, all right, before thinking about it or whatever, it's just like, does anyone just want to shout out like ballpark answer?
Positive.
Positive, okay, yeah. Positive what about?
Less than pi?
Less than pi, she says. Yeah, that's kind of important, right? Why less than pi?
Well, the box is like pi times 1.
Yeah, because there's like a pi times 1 box, and this lives inside a pi times 1 box. So yeah, okay, so pi. And maybe, can I get like a lower bound? More than pi, yeah, 0. Lars says more than pi over 2 because why?
You make a triangle from the origin to pi to that point. It's the side.
Yeah, using like some kind of common sense or some facts about sine, like I guess that it's concave down or something like that, right? And concave down curves lie above their secant lines. Does everyone see how that triangle is half of the box? So I claim that this is going to be somewhere in between pi over 2 and pi, yeah. So I usually like to do this actually before the FTC because it's more fun then because you don't know the answer. And maybe you don't know it now either unless you're stopping calculator, so don't do that. Let's just actually do it real quick. Okay, how could I, the problem I have here is if I was going to do this the old way, the problem is like I don't have summation formulas, right?
Yeah.
Yeah, but we can maybe just try to do it, like let n be 10. If n is 10, let's split this up into a bunch of rectangles and just like see what happens. So like what would if I split this up into 10 rectangles, what's the width of each rectangle? Pi over 10. So delta x would be pi over 10. And then so like the first one would be here, that would just be like pi over 10, right? You guys with me? And then the next one, just like shout some stuff out. 2 pi over 10 and like 3 pi over 10, etc. Okay, so, and then the last one will be like over here. So, okay, so that would be, yeah, pi over 10. This is 2 times pi over 10, 3 times pi over 10, etc. Until we eventually get to pi times pi over 10. Wait, no, 10 times. Oops. 10 times pi over 10, which is just pi, so okay. So I claim that this integral, the integral from 0 to pi of sine x dx is approximately equal to, well, let's just like do it. So it's just going to be, what's delta x? Yeah, pi over 10 times the sum from I equals 1 to how many rectangles now? 10. And then what's the height of the ith rectangle? Me?
Sine of I times pi over 10.
Yeah. Yeah, the sine of I times pi over 10. So far there's absolutely nothing different from anything that we had been doing. This is just another integral. The only problem is like I don't have formulas for like the sums of sines of things, right? Okay, so how can I do this? I'm going to cheat. I'm going to use a calculator. And I'm not going to be able to get the exact answer, but I'm going to be able to get an approximate answer. So you should take out. I don't think I did this in this class, or did I? Did I do this already? No, I didn't, right? I did it in third period or something, right? Wait, we did do this or we didn't?
I think we did, yeah.
Did I do this with the sum and the sequence and everything?
No.
Not with sine.
Wait, Power wasn't here.
Oh yeah. Wait.
Here's the
No,
Oh, wait.
Laura wasn't 85.
Oh, that was in that period.
She watched it over video.
Okay. Yeah, I thought that I didn't. I was pretty sure that I didn't get to it in this class. So okay, so that settles the mystery. Yeah, so I'm going to do that. That thing I did on the video, I'm going to do right now, Laura. So yeah. So here's something. And this is actually an interesting and sort of important calculator thing. So let's reset.
Hey, Mr. Rose, how do I tilt it up?
There's like some way. One of those like knobs.
Yeah. Okay.
But I don't know which one. Figure it out.
I'll try.
Ooh.
No.
Lift it up.
I'll apologize to anyone watching.
Could you just make the back like
All right. So,
true.
let's see. What should we do? Can I just type that into my calculator?
Yeah, it like doesn't
somehow?
work.
Does anyone know how to do like sums on their calculator, like sigmas and stuff?
Oh, that's like super smart.
If you do, I would be impressed. Yeah. You just like call yourself or whatever.
It's good. Yeah, it's good. It's good.
It is something
It's
in
terrible
math,
now.
right? So here's what you do. I'm gonna teach you a new skill that you probably don't know. If
Back
you
the fuck
hit-
up.
Sorry. If you hit second stat, better attention basically. If you hit second stat, otherwise known as list, and you go over to operations, there's this command called sequence. Everyone find it? And the sequence command, if you have the fancy new calculator, will enable you to input like expressions, you construct sequences. So, for example,
Wait, how did you get to that? You have to.
I have the fancy new stuff. If you don't have the fancy new stuff, just go with it. Watch, you'll see. So under expression, I'm going to put x squared, because let's just say I want a list of squares. And then under variable, you're going to list the variable which you would like to, your variable which is going to change, and the variable that's going to change is just x. And let's just say I want to start at 3 and end at 7. And there's an optional parameter for how much you want to step by, but if you leave it blank, it just assumes step by 1. And if you would paste, then, by the way, if you don't have the fancy new calculator, then you would just type it like that with commas. What this will do is it will construct a sequence from x equals 3 to x equals 7, such that the formula is x squared. And it outputs it as a list. Everybody cool? Have we mastered this? It's just like computer science. Nod gently if you're with me. Okay, good. All right, so that's kind of what we want to do over there, right? Make sure your calculator is in radians, because you have to be radians for calculus. And we want to add up, we want a whole bunch of numbers, each of which are of the form sine I times pi over 10. So I want to go list, operations, sequence, and now what should my expression be in general? Sine, no, not sine x. It should be sine of, I want my sequence to be the 10 numbers to be added over there. So it should be sine of x, yeah. Sine of x times pi over 10. You with me? That's going to be the number which gets added each time. My variable is x. I want to start at x equals 1 and go until x equals 10. And if I paste that in, now, and I hit enter, okay, it's kind of gross, right? What it's going to give me is a list, and there are 10 numbers in this list. And what are the 10 numbers? What is the significance of those 10 numbers? Or like, what are they? They're the y values, right? They're the 10 y values that I want to add up. So what I really need is like some kind of sum command. What I wish I had is some kind of sum command, Emma. So is there a command for that? Yeah, there is. It is under stat calc. No, where is it? Oh no, it's under math. No, what the hell is it?
It's
List,
in
operations,
yeah.
Math. Yeah, there it is. So instead of under operations, if you go to math, there's this command which is sum. And so what the sum command will do is it will sum all of the numbers in a list. All right, so if we want to do this from scratch, what we're really going to do is we're going to take, what we really want to do is we want to take pi times 10, or pi divided by 10, that's the number on the outside of the sigma, times, and then what I want to do is I want to sum, so I go list, math, sum, and what I want to sum is the 10 numbers in a list. So now we'll just construct that list over again. That list is operations sequence. It's the sequence, oh, it's still there. It's the sequence whose general term is sine x times pi over 10. The variable is x. I start at 1 and end at 10. Paste that in, and then I'm going to close the sum. And if I hit enter, this is going to pi over 10 times the sum of the entries in that list. You guys basically with me?
Whoa.
1.98.
What?
What do we think the answer is?
I think it's 2.
Maybe it's 2, right? Yeah. So how can we make this more accurate?
Infinity.
More rectangles.
Let's do like 11,
yeah.
Mr. Rose.
We can
11.
make it 100. What's up?
I think we should do 11 rectangles.
No, 11. Okay, 11. No, just kidding. So if you do second entry, we can change everything to be 100. So instead I'm going to go from 1 to 100 by doing the insert command, and then I need to change that to 100 also. That's like the general formula, and then I also need to change the delta x by 100. If we do all that, we should get a number. We should get something which is more accurate, and the answer is.
Whoa.
1.9998. All right, now I strongly feel that the answer is probably 2. If only there was some way for my calculator to just do this for me, because it's kind of like a program, right? So I kind of just want the number of rectangles to go to infinity. Well, there is a command. The command is math 9. Math 9 says fn int, which stands for functional numerical integration. Functional numerical integration essentially just does all the things that we just did, right? It takes the functions and splits them into a whole bunch of intervals, it takes all the y values, and it lets n go to infinity in some sort of numerical way. And when you type it in, if you have the fancy new version, then you get this little integral and you just fill it in, right? So we want the integral from 0 to pi of sine x,
Math 9.
and then we're integrating with respect to x. And the answer is?
2. Whoa.
If you have I kept it on old for years and years and years, but like I was the only one left in the class that still had the old version, so eventually I converted. But if you want to go old school, I will change it to back to classic. And if you change it back to classic, I can show you that.
Real sugar.
Those of you who pay attention to Math 9, and then you just do it, right? You looking up? I'm teaching you how to do this. F and int, and then you just do the function, which is sine. And then you're integrating with respect to x, and you go from 0 to pi. So it's really just.
Mine has the.
Oh, you have the fin. Oh, so you have the
It was really weird.
Good combo. Okay, follow. Kendall, good. Okay. So this is kind of awesome. This was like how these are our options for taking integrals, basically. We can either have some summation formula, we can use a calculator, or in the brave new world that we now live in, we can actually just use the fundamental theorem of calculus. And the fundamental theorem of calculus says that if you want to integrate from 0 to pi of sine, this incredible process, which involves taking this interval, splitting it up into innumerable tiny subintervals, taking a sample point from each subinterval, adding them all up, or multiplying by the width, adding them all up, and letting n go to infinity. This can be accomplished if we simply know an antiderivative of sine. Do you know an antiderivative of sine? Yes. Negative cosine. And so what we do is we say, all right, well this is negative cosine times, or evaluated at pi and 0. And with the fundamental theorem of calculus, this is now just doable, right?
Yes.
So this is negative, what's cosine of pi? Or I'll just write it maybe. So there's lots of, like, you have to be kind of careful with your parentheses. So it's like negative cosine pi minus negative cosine 0, I think, right? Yeah. So this is, what's cosine pi? Negative 1, so that's like negative 1, and then like plus cosine 0, which is 1. So 1 plus 1 is 2. So awesome. So awesome. Okay, while we're still on this topic, so this is sort of just another example of using the useful part of the FTC. It's just amazing that this works. There's another like kind of loose end I want to talk about. There was this accumulator function worksheet that we went over the front and we did not go over the back. I want to do that now. Do you tighten back up to like? I don't think I'm going to use the calculator thing again, so you can tighten it back up. Did you do the back of this accumulator function worksheet? You were supposed to. It was like the only homework that you had to do on FTC day. Let's see if he did it right. No, he didn't, because it's really hard. Here was what you were supposed to do, Stephanie.
Right? Yeah, it's fine. Yeah, it's good.
Okay, this could be another awesome experience for some of you. So here we go. I would like to, so this is my function f, and then I asked a bunch of questions about this. Oh, and then I introduced a new function h. We didn't actually go over this one. I used to go over this on FTC day, but I've actually found that it's better if we go over it after FTC day when we're sort of smart and like know some things. So okay. This was cognitively a lot harder than the problem on the front because now we're integrating not from -4 to x, but from 3 to x. So first let's just see if you've got all the numbers right. So can I do this really fast? H of 6, that's just the integral from 3 to 6, which is what? -9 pi over 4. Okay, good. What is h of 10? Well, h of 10 is just the integral from 3 to 10. So that is going to be, that's like 12, right? And that's 2. So it's going to be 14 minus 9 pi over 4. You guys getting these all right? Okay, but now things get kind of, no, and then h of 3 is just 0 because it's the integral from 3 to 3. Okay, and then here's when things start to get complicated. So what is h of 0? Well, h of 0 is the integral from 3 to 0 of f of t dt. But as we've seen, what is the integral from 3 to 0 of f? Yeah, it's the opposite of the integral from 0 to 3 of f. And what is the integral from 0 to 3 of f? Negative 9 pi over 4. So this is negative 9 pi over 4. So you guys got positive 9 pi over 4. That's the correct answer. This is just like basic accumulator function stuff. Someone stop me if you have a question. Okay. So let's just do the last two. H of negative 2 and h of negative 4. So h of negative 2, that's the integral from 3 to negative 2 of f, which is just the opposite of the integral from negative 2 to 3 of f. And the integral from negative 2 to 3, man, this is so complicated. Now this is like 2, so it's the opposite of 2 minus 9 pi over 4. So did you guys get 9 pi over 4 minus 2? Most people, that's good. Okay, last one, h of negative 4 is the integral from, from 3 to negative 4 of f, which is the opposite of the integral from negative 4 to 3 of f. And then the integral from negative 4 to 3 is just going to be, so this is the opposite of 4 minus 9 pi over 4. So it's 9 pi over 4 minus 4. Okay, now comes the weird questions, which is when is this function increasing and when is this function decreasing? Okay, let's do the easy ones first. So the easy ones would be, let's just start drawing rectangles. So let's look at h on the interval from 3 to 6. So on the interval from 3 to 6, so I start drawing rectangles, right? And if I start drawing rectangles, remember the question is, if we want to answer the question, am I increasing or decreasing? We move to the right and we figure out what h is doing. What is h doing as I draw these rectangles?
Decreasing. No.
Okay, yeah, that's true. But is h increasing or decreasing?
Decreasing.
Yeah, h is decreasing because I'm drawing negative rectangles. I think that's pretty clear, right? So I'm going to just write that here. I'm decreasing on the interval from 3 to 6. H is. Okay, I'll just write h decreasing. Okay, and then how about on the interval from 3 to 4?
Increasing.
Now I draw a little rectangle. H is increasing, right?
Yep.
Okay, and it just keeps increasing all the way. Okay, so I think I got this under control. All right, it's when we start going backwards that things get really weird. Okay, and now I'm gonna say some things, but it can't leave this room or something like that, right? Like I'm gonna speak to you in language which is very informal and unmathematical. So we're just gonna talk it out, but the kinds of things that we talk about for the next 2 minutes, you should not write on tests or AP exams. This is special. This is special. Sandeep, you know you have sometimes. Actually, forget it. I'm not gonna go there.
Are we sharing?
Sometimes you have special talk with a special someone that you just keep amongst yourselves. Yes.
Are we sharing this with the internet?
Oh, also sharing with the whole internet. Yeah. Okay. So here's what I would now like to know what happens on the interval from 0 to 3. Is this function increasing or is it decreasing? Okay. This is a really weird question to answer because as the answer to whether h is increasing or decreasing is the answer as to what happens as x is getting bigger, right? So we have to let's position ourselves at x equals 0, and then let's trace what happens as x goes from 0 to 3. You with me? Okay, so if x is at 0 currently, then it means that we have like these rectangles kind of already drawn. Right? Because that's kind of what it means if x is at 0. And what happens as x goes from 0 to 3 is that we like erase these rectangles. You guys kind of with me on that? That's
Wait, what? Yeah, wait.
right, sort of, almost.
Wait, why are the rectangles already drawn?
Because I'm sort of thinking aloud. I'm sort of asking the question on the interval 0 to 3, sort of what happens, right? Because I'm trying to explore whether this function is increasing or decreasing on the interval from 0 to 3. And in order to answer the question, is h increasing or decreasing on the interval 0 to 3, I need to sort of let x move, from 0 to 3. Right? So if I'm going to move x from 0 to 3, then I'm going to start x at 0. But if I start x at 0, that means I've sort of already done the integral from 3 to 0. And now what happens is, as I move to the right, as x moves to the right, instead of integrating from 3 to 0, I'm going to be integrating like from 3 to 1. And so I like erase a rectangle. Okay? So as we move to the right, we're erasing these rectangles. So you guys kind of okay with that? This is actually sort of a weird way to do it. Now we have to ask the question, how do these rectangles count, actually? Because they're upside down, these rectangles, right? This is the kind of thing you shouldn't write on the AP exam, like upside down rectangles. So do upside down rectangles count positively or negatively?
But do backwards.
But these are also backwards rectangles. Yeah, so this is like turning like a Roald Dahl novel or something, right? So now we have these like backwards. These are upside down rectangles, but they're also backwards rectangles,
so
right? So each of these rectangles contributes positively towards my integral, because on the interval from 0 to 3, delta x is negative and the function is negative.
So you're taking them away so you're counting negatively?
Yes.
So they're positive, but you're taking them away so they're negative.
So yeah. So is it increasing or decreasing?
Decreasing.
Increasing.
Wait.
Well, this is really hard, right? As x moves from 0 to 3, I am erasing backwards upside down rectangles.
We're increasing.
No, I'm erasing. I'm erasing backwards upside down rectangles.
No, he's erasing. No, because they're backwards.
They're also backwards.
Yo, he's erasing things, so it's decreasing, it's going down.
Yes.
Just remember, you're yelling.
Yeah, okay, you're erasing positive.
So the answer is it's decreasing.
No, because
as I move from 0 to 3, I'm erasing these rectangles. But each of these rectangles counts positively because they are both upside down and backwards. So if I'm erasing positive things, then I am decreasing the integral. The integral is getting smaller because I'm erasing upside down backwards things. Yes?
Why are you moving from 0 to 3 instead of 1 to 0?
Because that's what we mean when we say is h increasing or decreasing. By default, is a function increasing or decreasing implies or means as x moves to the right, what is the function doing?
So could you also say that when you're going from 3 to 0, you're erasing negative ones, which is positive, so it's backwards? Yeah.
Okay, yeah, you could. You could take out the negative and then do the problem. You could do that. Yep. All right, so how about, okay, let's I don't know if this is fun or just weird or confusing, but how about over here, now let's figure out what happens on the interval from -4 to 0. Well, if I want to figure out what's happening on the interval from -4 to 0, I have to sort of already assume that my rectangles are drawn, and then see what happens, because as I move from -4 to 0, I'm like erasing stuff, right? Okay, so now what happens as I move from -4 to 0? As I move from -4 to 0, I'm erasing rectangles. But are these positive rectangles or negative rectangles?
Negative.
They're negative rectangles because they're right side up backwards rectangles. Right side up backwards rectangles count negatively, and by erasing the negative rectangles, I am increasing the function. The function is increasing. Okay, yo.
So on the AP, we're not supposed to talk about like the backwards upside down.
You're
everything.
not
What
supposed
are
to.
we supposed to talk about?
What? Oh, okay, good question. So he says, all right, so this is an intuitive understanding. This is the kind of logic that I had hoped that you would have done at home by yourself before FTC day, potentially. But if you didn't, that's okay. But now, armed with the FTC, there's a quite easy way to do this. Someone tell me what I should do now that I actually know the FTC.
Apply the real FTC.
Apply the real FTC. She says just take the derivative of h. What is the derivative of h?
I don't know how to answer these questions anymore.
Wait, h prime just is
F of e.
f. Yeah, h prime is just f, right? That's what the FTC says. The FTC says that the derivative of h is f. And so we could sort of think of ourselves, we could sort of make like a sign chart for h prime. And we could sort of, so this is like -4, this is like 0, this is 6, and this is 10. And like if we are convinced that h prime is f, then the derivative of h is going to be positive on the interval from -4 to 0, negative on the interval from 0 to 6, and positive on the interval from 6 to 10. So it's actually matching the theory. Our sort of weird, intuitive, wishy-washy explanation is actually matching the theory exactly. And there's something even deeper that can be said about this, because after all, let's not forget about our friend g, which was the function on the front, which was far more cognitively easier to process. G was the integral from -4 to x of f, right? Is there some kind of connection between h and g? This is important, I would say. Eob knows. Eob, what's one connection between h and g?
They have the same what's it called, derivative, so it doesn't really matter where they start from. They'll increase and decrease in the same intervals.
Okay, so he says that the derivative of g is also f by the fundamental theorem of calculus, and so if we believe the fundamental theorem of calculus, this says that g and h have the same derivative, so they must differ by a constant. Can someone else bring it to me even in a more direct manner? By what constant do they differ by, actually? Express h in terms of g. Right, g is the integral from -4 to x of f. What can we do with that integral? Emma?
Well, it just is an F of e. F of x.
Wait, oh.
Wait, is
Oh,
g of x?
Yes. Yes. Break it up.
So,
Kendall saying something deep.
Oh, we're, yeah, 3. And then x, and then f of g, and then from 3
And then h max.
Yeah. Yeah, Kendall says, look, can I just split up the integral from -4 to x as the integral from -4 to 3 plus the integral from 3 to x? Of course I can, right? What is this guy on the left? This is just g. What's this? Well, it's some kind of a number after all, right? What is that?